Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Welcome back to the Neil Ashton podcast. Today's guest is Professor Max Welling, one of the foremost experts in machine learning, and I was speaking to him in this episode about AI for science, the use of machine learning and AI to solve some of the biggest challenges in science. Now, if you're in the machine learning world, you'll already know who Professor Welling is, but just in case you're not, I'll just briefly give his background and why he is such an expert. Well, as we actually discussed in the podcast, because I always like to ask people about their academic careers and how they got to, where they got to. He started off, the standard academic track, I guess, doing a master's and a PhD. And then, as he said, he actually did many postdocs, moving between different universities. I guess most notably, he was with George Hinton, who is seen as the sort of godfather of AI at UCL. But then he went over to the US, to UC Irvine, and he started being a professor there. And then he ended up actually going and being an assistant professor there, and then coming back to the University of Amsterdam to become a professor, and he's actually stayed there pretty much ever since. But one of the interesting things is that he has taken roots into industry and startups. So he was a VP at Qualcomm, and actually very recently he was also a VP and distinguished scientist at Microsoft. He recently left that position and to start a new startup called CuspAI, which is working on machine learning for material discovery in the topic of carbon capture. We actually go into what his startup's about, what they're doing, why he's interested in this area. I probably could spend a long time going through all his achievements, but he's one of those people who is, at the forefront of machine learning. So he's been the people in charge of all the major conferences like NeurIPS and ICML and iClear conferences. He has been leading, if people hadn't seen, and I would highly recommend that you do look, some of these workshops on AI for science, particularly at NeurIPS the past few years. So these bring together all the world leading experts on machine learning and its application to science and bring them all together in workshops. That's been really good. And what I like about him is he has that unique experience that we touch about, being not just a pure academic or being a pure industrialist, but someone who has jumped between. And I really do believe that gives him somewhat a unique insight into not just the science, but the practicalities of how do you go about it. And that's exactly what we try and discuss a little bit in this. We purposely keep it reasonably high level, so we're not going into the super details, but rather looking at the big topics. So, for example, we start off by discussing data-driven versus physics-driven approaches, as in, do you need to include the physical equations into the loss functions, into machine learning, or can you just let the data do it? We talk about foundational models, as in, could you create a foundational model for science that you can just use or just fine-tune? And then we pivot a little bit, and what I think anyway, at least, there's some interesting discussions around, should you open source the models and the data? We have a good discussion about the merits of that, ethical considerations, etc. And then we get into the different modes of operation. What are the advantages of academia, industry, and startups in terms of reaching these benefits? We talk about his startup, about CuspAI. We talk about what they're doing, why he's doing this, his excitement and motivation to going back to a startup. We briefly took on some of the funding. What's it like getting funding from VCs in Europe versus the US? And then we sort of finish a little bit discussing career paths. He goes into more details about his personal journey through academia, through industry, his advice for people now, and finishing really on what his thoughts are on the future of machine learning and how this could help scientific discovery. So a pretty wide-ranging topic, like anything. We probably could have spoke for many more hours, but I certainly learned a lot through this conversation, and I hope you enjoy it too. So sit back and please listen to this episode with Professor Max Welling.
So we started now?
We have.
All right. AI for science, I think, is the application of the tools that are being developed in machine learning and AI to basically help the discovery process and the analysis process in the sciences. The interesting thing is that there's also science for AI in a way, which is using principles from the sciences and the mathematics, such as symmetries, diffusion processes like thermodynamics, to build better machine learning models. So this thing actually goes two ways. The causal direction is going two ways. Now, what we see is that in the sciences, in a very broad spectrum of the sciences, going all the way from the very small, picoseconds, femtometers, which is basically high energy physics, where a lot of machine learning is used to do data analysis, all the way up, let's say going through molecules and liquids and fluids, and then all the way to sort of earth sciences, and maybe going all the way up to astronomy. Which is at the scale of the universe. Machine learning models and methods are being used to model that particular domain, but also analyze the data better. So it has been having a huge and very broad impact in the sciences, I would say.
And how much overlap is there, would you say, between the work and the methods that are being used to develop, let's say, some of the large language models and those which are in the sciences? Is it a matter of applying the same tools and technologies and it's just essentially a different focus area? Or do you see that fundamentally there are differences and new approaches that need to be developed?
There's a surprising amount of overlap, I would say, which I find interesting. So the first thing to say is that even within this incredibly broad range of scientific disciplines, of course, the tools that are being used, the mathematical tools that are being used, are often very similar too. So you start from, it's either a partial differential equation or a stochastic differential equation or ordinary differential equation. That's because physics is causal. You try to predict the future from the past. It's typically continuous, but not necessarily. But many, processes are modeled continuously, like fluids. And it's local, which means that you typically don't have something at a very far distant place instantaneously impacting things here. And so these three aspects make the tool set typically quite similar, even across all those scales. So now to the question, some of these tools which are being developed for image generation, perhaps more than for large language models, so that they're actually different tools, although they're all being, put in the same bucket typically as generative AI, but actually quite different. But especially the methods that have been used for video and image generation, which you can actually somewhat think of as a physical object with pixels being microscopic degrees of freedom, which have some dynamics. So the tools and diffusion models, for instance, which is the method that generates all these beautiful images and videos these days, those can be almost literally used to generate molecules and fluids. So maybe not surprising, because a fluid you can think of as a sort of a set of pixels, or it's typically modeled as a set of pixels, that evolves over time as well. For molecules, you could argue, those are, it's more like a graph where the nodes are at certain locations. So maybe they're slightly more surprising, but it is almost literally the same tools. In fact, we developed what what's called equivariant methods, which incorporate the symmetries of the world, which is that a molecule or an image. So it may be best for an image. If you look at sort of a histopathology slide, which is a slide which has all these kind of stained cells in them, and some cells might be have a tumor in them and other ones don't, and your task is to find the cells which are malignant. So if you turn the slide upside down, you don't even know, right? It's just the same set of cells, but just rotate a little bit. But a neural network doesn't know that usually, and so we've built models which were called equivariant, which build in this sort of symmetries. So, for instance, those methods, these symmetries which we've developed for vision, very naturally also transfer back to physics. So they came from physics in some sense, and we turned them into tools for images, and now we apply them again to molecules, right? And so a molecule upside down is the same molecule, or a molecule displaced from here to here is still the same molecule with the same properties typically. So that's why these tools are very useful, across the board.
But one of the topics that seems to be very much an active debate at least in the machine learning for fluid dynamics, which is maybe what I'm most familiar with, but I'd be keen to get your opinion on this, and more broadly to other scientific disciplines, is this sort of physics-driven versus data-driven.
Yeah.
I see on one side the logical argument, there are physics laws, surely the solutions should bound by them. But I saw you gave a talk recently, and you were alluding to the idea of there's a sort of cutoff point where if you don't have much data, maybe it makes sense to use them. But if you have a lot of data, you may even be constraining the problem and solving it. What are your current thoughts on this debate around physics or data-driven approaches?
Yeah, very similar. So I agree with my older self, so that's good at least, so some level of consistency. So for instance, when I was still working at Microsoft with a wonderful team there, we worked on models for the atmosphere. Mm-hmm. And this was recently published as a paper called Aurora. Mm-hmm. So there is a lot of data. So that it's like petabytes of data because we predict the weather every day, every hour, and we store all that data. And then, of course, we know what the actual weather was. At least we have measurements. And so it's a very rich annotated set of data in some sense. In that domain, you can basically let go of all the laws of physics. You can just say, let's think of this as a big machine learning problem. We just try to predict the state of the atmosphere, a day ahead, 10 days ahead, whatever, right? And you can just use your transformers and everything that you use for image and videos as well. And that worked really well. In fact, it's basically as good as numerical solvers. I should be a bit careful saying that, but it's as good with if the prediction stays within the sort of the input that it was trained on. If it goes far beyond that, you have to be much more careful, of course. But the big advantage is just that's way, way faster. So it can be up to 10,000, like 4 orders of magnitudes faster. Mm-hmm. Now, there's other domains where this is much harder, where you don't have this huge amount of data, in fact. And in that case, you should really build in what we call inductive biases that are coming from the laws of physics. And I've seen some interesting examples where, for instance, we know the continuity equations should hold, typically. Mm-hmm. If you write down sort of the Navier-Stokes equations, many of them have the shape of some kind of continuity equation. So that's the partial differential equation that describes basically a velocity field over which the fluid moves in 3 dimensions. And then there's a source term, basically, which, applies extra forces to that. And so sort of if you do it with the transformers, it has to learn all that. But it makes a lot of sense to say, well, we know the world is 3-dimensional and it has this sort of, and we know how fluids move around. We just may not know precisely what the forces are that are acting on them. And so we learn the forces, but we constrain it to be a fluid that moves around according to the laws of physics. And there, if you have little data, then that's a very good prior. Now, the flip side is there's always a flip side. So if we don't know the precise laws of physics at that scale, even for the weather, right? We've written down, or the meteorologists have written down, and I don't know, order 10, 20 equations which describe all the complicated interactions of the atmosphere with, the surface, with, the radiation, with chemicals and all these things. So everything is written down in these equations, but these are approximations. They are not actually, we might know the laws of physics at the very microscopic level, how one atom sort of interacts with another atom using quantum mechanics and all that. We know it very precise, but it's completely hopeless to simulate the atmosphere at that level. So we have to coarse grain is what we call it. We have to go to a much more less precise level of description. And at that level, things become approximate. And so if you impose more and more laws of physics, which you've approximated, at some point you might have so much data that you sort of build in a ceiling to this modeling. You say, I want you to fulfill these constraints, but if these constraints are approximations, at some point that means that you cannot get out of that box. And if you have so much data that the model can actually learn something that's more precise than that box, than those constraints you're giving it, then you're constraining the model, you're over-constraining the model, and that's hurtful.
All of these, at least from what I can see, most of us, when we use a large language model, we never need to train the model. We are just doing an inference, essentially, on a pre-trained model, a foundational model. And most of us never need to train it ourselves. Whereas if we take a fluid dynamics or a weather problem, do you think that we will ever be able to get to a truly foundational model, which is trained on such massive data that it could work for a plane or a car or a building, or the weather could be done in different parts of the world or anything, or is science a problem that's just much more challenging than what we've done for the large language models to date?
Yeah, it's a very interesting question, I think. On the one, so to me, this kind of I think it does make a lot of sense to train a very large foundation model, and this means plenty of evidence now that if you collect data from very different domains, different regimes, pre-training such a very large foundation model is a huge benefit, especially if you can then fine-tune it to the particular problem that you're interested in. So with a little bit of data and a little bit of fine-tuning, you can get a very good model. So I think that's a paradigm that has now been established. I think that's, I think that will just work for the foreseeable future. But there's also this thing that which are called the 80-20 rule, which is that it's 80% of getting it right is quite easy. You can do it with 20% maybe of the effort, but then the last 20% is incredibly hard. And you need a lot more effort, right? And so I think you can see this very clearly for self-driving cars, right? So in self-driving cars, people get very enthusiastic for the first 80% because, hey, we can drive a car without hands on a street. How wonderful! And then you realize that to get it to drive inside Amsterdam, that's not going to work with that first, with this first, model you have. And so you now need an enormous amount of training, but actually probably just rules-based methods as well, to make this thing drive safely inside a complicated city like Amsterdam. Maybe San Francisco works. I don't know. The streets are all rectangular and everything, but in Amsterdam, it's all big chaos.
Bikes, right?
Yeah, people run red lights, bikes everywhere. It's like massively complicated. And so it will take 80% of the time maybe to get this long tail of issues correct. And this is where humans really are very good. Somehow, and this is to do with this generalization, somehow we do this very naturally and very good. Now, in large language models, I'm sort of seeing something somewhat similar, right? Which is we can get amazingly good at, I didn't predict this, to be really honest, to build these chatbots. but it is perhaps 80% of the way. Now the last 20% is you should get it such that you can't trick it into saying all sorts of rubbish like, put glue in your pizza or eat rocks, right? These are the kind of things that our big tech companies are now struggling with because, if you put this out there, people will try
Mm,
to game it. And that's very negative publicity and all that. So this last 20% to make it really understand common sense, it's arguably whether this even can be done by just looking at text. Maybe this needs to be some system that grows up among humans, with a body and sort of interacts with humans and understands social interactions and
mm,
ethical rules and all these kinds of things. Maybe it's just you cannot just learn that from text, and that last 20% might be very, very hard. And so perhaps in physics it's the same, right? So you can get it right 80%, and that hopefully is useful. But
mm,
then how do you protect yourself against that 20%? An unseen initial condition with incredibly important consequences. Like, okay, we might just get a heat wave, 50 degrees Celsius. Do we warn the public?
mm,
Or do we not, because we don't know precisely what's going on, right? And that, I think, is incredibly important to get right, and we haven't really get our heads
mm.
around how to do that. And I think uncertainty quantification and reliable uncertainty quantification is going to be key for that.
Yeah, very interesting. I haven't really thought about it that way. It's true, the 80-20. And now I think about it, how I use these large language models is I very rarely take the exact output it gives me. I normally will iterate on it, but it enables me to get somewhere much faster.
Yeah,
I suppose maybe from the physics side, we're expecting it to get perfect, where really maybe our expectation should be more similar, that it gets us somewhere closer, and maybe then we feed that solution into a traditional solver
precisely.
to do the next bit.
And initialization, like a smart initialization or something. Yes.
Yeah. But all of this, I still wonder about the data challenge, because it seems, because of the internet and maybe things have been clamped down, so many images and so many text are publicly available that you can get. Whereas with science, it's very rare to have so much of that data in the public domain. Most companies have that behind firewalls. Even people publish papers, but they very rarely publish the entire data that created it. So how can we get around that issue of the data?
Yeah, that's the absolutely key. So that's the key for progress, I think. So you can see that the domains where you know researchers have managed to do a lot more data sharing, or where there's just more data available, have progressed fast. Certainly, with machine learning tools. But for many other domains, companies are hoarding that data, or even universities are hoarding their data because it's expensive to generate, and they want to, milk that cow for a couple of years in terms of papers before they give it to others. And so that is really slowing down science and progress. There is great initiatives where, for instance, in bio, where people are sharing a lot of data. There's a lot of
Mm,
omics data available, etc. So there's also good examples. There's the materials project, for instance, and other materials projects around the world where data about materials are being collected. But I think in the end, we will have to invent a technology that makes data sharing much easier. And I, would envision some kind of marketplace where people have their data behind a firewall. But if I want to train a model, I just go to your data source, and I'm going to say, I'm going to pay you whatever amount of money
mm,
to access your data source. Now, note that I will do it in a differentially private way, which is
mm,
to guarantee that I'm going to update my model parameters, but I'm going to do it in such a way that I can never reconstruct data that were
mm,
used inside your data source to build my model. Now that can be guaranteed, but that technology also needs to be improved. So that means that, your agent and my agent, they negotiate a bit about the price, and then I enter, do my model updating, and then I move to the next, data source, right? So now we can train really excellent models, but there is kind of trading going on about how much that is worth. In fact, you could do it for your own data. So I could say, I've collected all my data over my lifetime, including my medical data, whatever. I'm quite happy to help that hospital, let's say, for free. But when Google knocks on my door, I want money because I
Yeah.
want a fair share, right? And so basically this means, or actually for OpenAI kind of, chat GPT
Mm.
models, right? Just like they now sort of, there's lawsuits now, right? So basically, it's unclear, what these models, like, I think there's this recent lawsuit against some of these companies that generate songs
Yeah.
from songs that are being created by artists. And so these artists feel, I've created this content and it's being, and somebody else runs away with it, where am I in this process? This is a fundamental problem that we have to solve now. And it would be much better if an artist, or a person who collects data in any way or generates content or data
Mm.
gets paid in a reasonable way, or can choose to make their data available to somebody who wants that data to train their models on. This is a fundamental problem across the whole machine learning and AI thing, that space that needs to be solved.
That's fascinating. It seems very interesting and maybe complementary, but in some ways also at odds. In that, on one hand, there is a movement of open source, open data, open source. So the idea being that everybody should make their data sets available. And I believe that some of the weather forecasting companies who released those data sets are now debating whether the next data should be closed and not open. Because it's true that many companies now publish models, have great success, but the people who generated the data have no financial reward for that.
Exactly.
And I feel that for the sciences, particularly most applications of science get into industrial use, where there is a commercial side to it. So just saying open source your data, well, they're probably not going to open up their data. So that's a very interesting point about a way of people sharing their data, but also being able to make money and privacy. Because I can't see a way of, let's say, fluid dynamics. Why would Boeing release all their aircraft data for training? Why would Airbus? Why would anybody else do it?
It's their competitive advantage. Yeah.
It's a competitive advantage, which is why I'm always wondering. And then universities typically do more fundamental problems. So if you train the data on just university data, it's only going to work for simple test cases, because universities are incentivized to publish pure research typically, not full aircrafts. Yeah.
I think the blockchain could play an interesting role here somehow, right? So you could imagine that you could sort of, I believe there should be some kind of marketplace for data. So first of all, we have to realize that data is perhaps the most important, resource.
Yes.
It's kind of the new oil on which these machines, drive and compute, I guess, right? So it's compute and data that these machine learning methods need. And we just need to put a real value on it. We have to say, it is valuable if you share your data or give your data. Just pushing people to put it open source I don't think it's going to happen, because everybody will always, do what's good for them. And we just need to make the incentive structures correct. I think that's the thing. You don't force people to do things, just make the incentive structures correct. So people who are open sourcing their data probably, they work at universities or they work at companies, and then the open sourcing works for them somehow anyway, because even companies who are open sourcing their stuff probably do it because in the long run it will benefit them as well. So,
what is your general opinion of that open source though versus closed source? It seems to be a bit of a debate in the community of, does it help science to open source, but then how do companies fund themselves if everything's open source, and how easily can it be copied? Do you have a thought on the optimum approach that you've seen different companies over the years take?
I mean, are you talking about open sourcing data or open sourcing their models?
Models more, but yes, I guess also. Well, we just discussed the data, but how about the models themselves
Well, I guess the
or
discussion
the
is about
architecture?
whether it's dangerous to release a model, right?
Hmm.
Because the model can be used for adversarial purposes and is being used for adversarial purposes. So you have to be careful that if you enable bad agents to do
Hmm.
horrible things, you just have to really think about that. So, in other words, if I would have the recipe to build or in a lab, a terrible disease that can be, unleashed on the world, I'm not going to argue for open sourcing that knowledge. Clearly, I just don't want that to be open out
Hmm.
there. And so you could argue similar things will apply at some point to machine learning models, or actually maybe already. I mean, these models can be used for phishing attacks and all these kinds of things, right? Or crime where you sort of
Hmm.
basically imitate somebody's voice, and then you ask them to, pretend to
Hmm.
be your son, and then ask to give some money. So you have to be extremely careful about when you open source something, and maybe there just needs to be some kind of ethical board that decides whether a particular very powerful technology can be open source, yes or no. Now, within that, once if you're within those bounds of safety, um, it's up to everyone to open source. You cannot tell a company to open source or not, right? It's like I
Hmm.
think it's not a very meaningful question to say companies
Hmm.
should open source their stuff. Because of course they won't if it doesn't improve their bottom line.
Hmm.
So it's up to them to open source whatever they need to open or want to open source.
But maybe a more specific question then: Is there a can methods move faster that have been open source because essentially you're outsourcing the development to a community effort, or is it the case that that sounds nice, but you can actually move faster by having an internal team with their own developers? Do you see what? Do you
Yeah,
see the?
yeah. So I think thinking very hard about the incentive structure. So if it's true that if you're a whole number of a small player cannot compete with a big player, right? So it does make a lot of sense to put a whole bunch of small players in a group, share resources and compete with the big players. Let's say you all build one huge large language model within your group of smaller players, and then everybody benefits from that large language model, and now you can compete with the big players. So that's a clear incentive to share in that group. Now, there's also other reasons why people might want to share, which is like we're all stuck with a problem together, which is climate change, right? So for some strange reason, we think that um, we can pollute this earth and push carbon into an atmosphere, which is a shared resource, but not pay the bill basically for
Mm,
doing that, right? We somehow think that's okay to do, but I think there is a sort of ethical awareness within a lot of companies, big tech companies, definitely, who are saying, well, we should all act together to do something about that, right?
mm.
Most of these companies have climate sort of promises, or what do you call them?
Sustainability
Yeah,
goals, do you mean?
sustainability goals and things like this. So to be carbon neutral or negative by 2030 and all these kinds of things. So they're trying, although they're tied up in an AI arms race, and so it's very hard
Yeah.
to actually make those goals. But let's say
Yeah.
they're trying to do this, and so there it makes some sense to pool resources, I think, and say, okay, let's be good actors in this world, with good citizens, and actually,
Mm.
release some of the data to the public so others can, help, for instance, improve the technology to capture the carbon out of the atmosphere.
Mm. The I wanted to maybe pivot a little bit to talk about your new company, but maybe as a way of getting there. One of the things that I admire about what you've done, and I'm always interested to hear the different logic, is the role of academia industry, big industry, like big tech companies and startups, what can a university achieve? What's the advantage of a startup, essentially? What drove you to create this new company? Is there a specific thing I can just move faster by doing it as a startup versus... I'm interested to see how you've seen over your career the sort of benefits of these three different places.
Yeah, I find it very interesting. There's this really three modes of operation. I've tried all of them now, so I've sort of sampled them a little bit. Now, universities have a very special role of educating the next generation of talent. That's really important, and they use taxpayer money for that, so that's incredibly important. But they also do sort of much more exploratory research, right? So they can if you like to think about the inside of a black hole, fine, do it in a university setting. There's no company that will. Well, there's very few companies that will fund that in some sense. Basically, no, I think at this point. But the impact is very diffuse, right? So you write a paper, and that paper gets picked up maybe by different groups, and they build on it, and that's a very indirect but important way to make impact. And it's also, of course, it's also a different style of doing research and being engaged in intellectual activity. Now, the big companies and the startups, they can command much bigger resources to really go after a specific target, right? So, no, but they're commercial, right? So they're tied to commercial goals. And so you have to really align the commercial goal with the thing that you want to achieve. Now, some people, if you like to achieve AGI, great. So you can work for one of these big companies. That's a perfect alignment because that's what these big companies want to do. They think they can make big money on that. So, that's where you can sort of do that research. And you can use the actual resources, like massive amounts of GPUs, to achieve that. But big companies are also, in a way, slow and political beasts, right? There's a lot of people that need to, agree on something, and a lot of legal involvement if you want to change something small, and so it's very viscous, this whole thing, right? Talking about fluid, it's very viscous thing. So the great advantage of a startup is that you're your own boss. So if you have a vision, you can execute on your own vision, and you don't have to constantly calibrate with other people higher up in your organization. You just need a great set of co-founders and a great team to execute who are aligned with that vision, and then you can really go. So to my surprise, perhaps, is that the amount of resources you can get in a startup these days in the field of AI is no less than what you would get in a big tech company. So, in fact, if you can tap into VC capital, I've had until now incredibly positive experiences with this, which means that first of all, these are very smart people. Of course, they want to, of course, get return on investment. So there's no idealism here mostly. But they're very smart people. They help you find a market. They help you build a healthy business. And there's lots of money available as well, right, for that particular purpose that you want to pursue. And so I think the agility and also the positive attitude that you find in startup land, I really like. So I guess I've now converged on that particular model, and I'll stick with that now for a while.
And just before we get into the specifics of your company, is there any differences or challenges between, let's say, in your experience, US, Bay Area, Europe? Are there advantages, disadvantages in terms of finding the staff, finding the money?
Well, we actually do use American and somewhat and English VCs mostly. There's also a few continental Europe Dutch investors, but mostly it's we're tapping into UK and US based VC firms. Although our lead investor is actually a UK based investor. So so I don't think you need to make that distinction in some sense. The
Okay.
nice thing is that these big investors, they're turning their side to Europe. And the reason is that there's just incredible talent pool in Europe. Many of many of this talent pool likes to stay in Europe because just Europe is just great, just a fun place
I
to
would
be.
agree. Yeah.
And the salaries are a lot lower than in Bay Area.
Yeah.
And so with relatively little investment, well, less investment than what you would have to invest in Bay Area, you can get a excellent team.
Hmm.
And so it only makes a lot of sense that also these investors turn their eyes on Europe. So I think we will see a lot of growth and activity in these sort of startup and scale ups in Europe in the coming years.
Mm. I've often I tease some of my American colleagues that why are they all based in Seattle? It seems like the most crazy time zone and position in the world to have such a. If you were going to invent a company to have a global reach, surely you wouldn't put it there. I still don't understand how this.
Well, it's something to do with ecosystems, right? So
Mm,
and that's really the thing. So if you build a particular nucleus or a particular geographic area where it's lots of things are happening, right? In Silicon Valley, you have the big universities like Berkeley and Stanford, um, which are providing a lot of talent, and there is a lot of entrepreneurial spirit in those
mm,
places, and there's a whole. Think of it as a supply line sort of issue, where there's a lot of other things which work for them. So there's a very small, everybody knows each other in the VC. So there's a lot of VCs which can fund these things, and you know,
mm,
so I think it has to do with the fact that once you build a really good ecosystem locally, it it then becomes very attractive to be there to do your startup. Because
mm,
it's very easy to get good ideas from, people help each other to grow these startups. It's a very collaborative atmosphere. It's
mm,
easy, if I need a new investment, I talk to a few people and they point me to other people, and then you're before you know it, you're in front of new investors. So I think that kind of lubricant in some sense is really good in these ecosystems. So what we need to do in Europe is to build these ecosystems. And I think in Cambridge and in London, these ecosystems exist, so they are very good as well. Amsterdam, Berlin, some other places, Paris for sure,
mm.
maybe Stockholm. So some of these places in Europe also start to develop these ecosystems, but we need to get better at that in Europe.
Mm. Yeah, I do definitely agree that there seems to be a lot of very talented researchers and engineers and scientists in Europe that maybe feel a pressure to perhaps to move to the US, where probably a lot of them would probably rather stay in Europe if they could do.
Mm.
So I agree, there seems to be a desire, and if you could tap into that, you've got a big pool, and the other benefits of time zones and access to different markets. But yeah, I'd love to learn more a little bit about your company, and maybe also, I think listeners of this podcast may be a little bit more familiar with some of the topics we discussed around fluid dynamics. So it would also be good perhaps for you to align how some maybe the material discovery and material science has some overlaps and maybe differences to
Yeah.
fluid dynamics.
So the startup is about material discovery for carbon capture, and so we focus on sort of a family of molecules called metal organic frameworks. These consist of sort of you can think of them as a sort of a lattice structure with on the nodes you typically put some kind of small little molecule piece with a metal in it, and then they get connected by organic linkers, is what they called. And so there's a huge design space, like many trillions of possible things that you can sort of even imagine with very different properties. And these frameworks, if you blow, let's say, air through them, they tend to bind the molecules in the air to the framework. So, for instance, carbon dioxide binds, but hydrogen,
Mm.
water, sorry, I say water also binds, nitrogen binds. So all of these molecules bind to them, and you want to find the metal organic framework that preferentially binds carbon dioxide relative to water and nitrogen and all these other molecules. And then you want to do this at a particular temperature and pressure, and then you change the temperature and pressure. Let's say you have less pressure and higher temperature, that would sort of release then the carbon again, and then you can sort of sequester it and sort of put it away or reuse it for something. So that's the basic idea. And now we are going to use machine learning to accelerate that process a lot. Right? So we can use these same generative models that are being used to generate images to generate new materials. And then we're going to test those materials in a chemistry pipeline, but those are also infused with machine learning methods to speed up this testing framework of how good this particular proposed material is. And then we have a search agent that tries to, orchestrate this searching through the space of molecules to find the best molecule with certain properties as quickly as possible. And so how does this connect to fluids? A gas is not quite a fluid, but you could imagine actually a fluid in a MOF. That's actually what happens. So you can also put fluids in MOFs. But let's imagine a gas where you can sort of describe a gas by somewhat similar equations as a fluid. There's sort of an equation that describes how this gas would blow through this particular framework, and then and how it binds the molecules to the framework. So that is not very unlike how you would simulate a fluid, maybe in some space with certain boundaries or something.
And how do people do it now? Because there are companies trying to do these so are they relying on more traditional physics-based simulations to do these discoveries?
Yeah, so there is already people who are having these kind of pipelines. So they're mostly chemists. So it's a chemistry pipeline or workflow where there's a database of known metal organic frameworks, and you push them through a chemistry simulation pipeline that sort of simulates all the molecules as they wiggle around in this particular environment, and then you can sort of measure how many of them would bind at certain temperatures and pressures, and that turns into a number that says how good this thing is, and then you have some somewhat simple way of searching through the space. Now you can see that can be massively improved with machine learning techniques. That's why we think it's such an exciting field, because they are not generating new materials with diffusion models. They don't use very sophisticated search algorithms either, in order to do the simulations for the ones that are important. And you can even accelerate these simulation models by predicting the properties directly using machine learning models, or by what's called training force fields. These are methods that compute the forces on atoms as they wiggle. Typically, you have to do this with quantum mechanics. It's very expensive, but you can do it with a machine-learned force field, which is, again, way, way faster, many orders of magnitude faster than a normal force field if you use quantum mechanical calculations, but almost as accurate as that quantum mechanical calculation.
Okay, interesting. And what made you target this area? Is it more as the climate change sustainability angle? Is that sort of a personal thing of yours that you've wanted to do? Because I know you've had a focus in many areas of science. I'm just wondering what made you focus on this area in particular.
Yeah, it's definitely a personal sort of preference for me and my co-founder, Chad Edwards. But also we think there is a big market for this, because I think companies do want to be a good citizen and compensate their carbon emissions, and at some point it might actually be enforced by government, which is what I hope. We need to tax pollution, and then having a solution available to actually capture that carbon is then going to be a big market, I think, as well. So it's an alignment again between something you really want to do and work on with a commercial angle, because otherwise you cannot build that company, a healthy company that will actually make that impact. So that's the way I view that. But having said that, there is many other directions in which this platform could be pointed. Even for metal organic frameworks, you can store hydrogen, you can catalyze, you can sort of deliver drugs, you can detect toxins, you can clean water, and that's only metal organic frameworks, right? But then we can also go to other markets at some point that are completely different materials.
And how does it feel? I think you alluded to what many people who work for large companies feel, which is the benefits of working for large companies, the access to a great talent pool, but maybe the slight slowing down and sort of meetings to decide other meetings. Have you felt a certain sort of energy of being back in a startup again?
Definitely. I've definitely felt a lot of energy being back in a startup. It is, I think it is no comparison in terms of, the way in which, you can motivate people to all work on this problem. And it's a somewhat small group at this point, of course. When these companies grow much bigger, there's also, of course, how do you maintain that spirit? It's not so easy, but as a startup, that's very special because you're small. You want to change the world. You have that vision to do that, and you can do it quick and fast with a lot of money actually under your wings. So it's a big responsibility on the one hand. On the other hand, it's also an incredible opportunity, and and really a little bit of a different feel than working in a big company.
Yeah, I wanted to pivot a little bit to get your advice, really, and some of your mainly your advice, I guess, to people who are early on in their careers. I think you've had a very interesting trajectory and kind of movement. What would you recommend? So if you're going back, you're doing your undergraduate degree. Let's say you've already decided to do a PhD. Would you recommend go do a postdoc, try and go the academic route? Would you suggest to go to a startup? How do you navigate this for people who wanted to sort of follow in your footsteps? Is there anything that you would do again or do differently?
So I should say I did many, many postdocs, right? So I did. I graduated in '98, and then I did a couple of years at Caltech, and then I did another 3 years with Jeff Hinton and do two different places, and I just loved it. So the first thing I want to say, it depends a lot on who you are. And also, that really suited me at that stage in my life. I was incredibly interested in fundamental science, and I didn't get paid a lot at all, but I didn't care at all. It was a beautiful life, having very little money to spend and just being a scientist. So these days, but I didn't have that choice, right? So that was actually different and interesting. So these days, it's much harder for young people because they see, this other opportunity clearly in front of them, right? And they say, I could either do that, and earn like 10 times as much as I can earn there.
Yeah.
Is it worth for me to just do this academic route? And, honestly, working in academia is also not all positive, right? At some point you're asked to juggle many balls. Like you have to write grants, you have to teach, you have to basically run your own business, you have to be good with people, a good manager, you have to be good at research, you have to be good at everything basically, and then you don't have job security until you get tenure. It's really in that sense a pretty lousy deal if you think about it. So you have to really want it. You should be an educator. So the good thing about academia is it's great to work with young people, right? It's fantastic to help people grow. And I still sometimes get emails from people, I was in your master class then and then, and it's because of you that I took this route and I now have this fantastic job, right? That is, unbelievably rewarding to get that. And that's what you have in academia. You can help people grow. You can turn them into great researchers. And you can see them have stellar careers, which is very rewarding, I think.
Mm.
So, is that if that's you want to work on the inside of a black hole, what's going on the inside of a black hole, and you like to work with young people, and you can put up with some annoying nuisances in academia, then academia is your thing. I honestly believe, and you should, and especially, you should not worry about money. It's easy for me to say now, but I didn't do it then. I didn't worry about it, but it was the best thing I decided because I could really focus on, building a good foundation for science, learning a lot about different topics, and having a sort of a research strategy for myself. So I think having a postdoc under your wings is really fantastic. And I don't think if you're a good postdoc and you publish well, it's not a disadvantage either, I would say, at all. But you can also do something else. You can also first work for a startup or first work for, for a company and then go back to academia. You should feel free to, you're not closing any doors, I feel, going back and forth between these things. Maybe make sure you publish now and then something exciting if you want to go back to academia.
But do you think there should be more, that the complaint I hear, or the issue is that postdoc, the funding model, the contract model is such that, as you said, for a certain time period, you can sort of deal with it. I don't know from my own experiences, but there comes a point where you're sort of, you want to buy a house or you want to get married or something. There comes a point. Do you think universities should do more? Or is there any way that you can do more to sort of keep those researchers who are great but give them more security, or does that break just the model of how universities work?
Yeah, I don't know. That's a very hard one. So in Europe, especially in the Netherlands, tenure isn't, it's very likely you get tenure, right? There's even something that was only recently introduced in some sense, but I've never seen people not get tenure. So it's not at all like MIT or Harvard where, I don't know, half of the people get kicked out or something. But then if you're kicked out of Harvard, you still have a great career afterwards, right? Because you work at Harvard in the first place. So yeah, I've never really worried about tenure and all these things. I went through the tenure process in the US. Maybe it's just blissful ignorance. I just never worried about it. But whatever happened, it happened, and just take the next step. I don't know whether we can give postdoc permanent positions because that's not the definition of a postdoc. So what we have done at the University of Amsterdam a little bit is to allow people more like flexible contracts, right? So for instance, you could say, half of my time I'm a postdoc, half of my time, that particular construction doesn't exist. But you say half the time you work in a startup, half your time you work at the university or something like that. I think that could be very helpful because half of the time you can make a lot of money, working in a startup or a big tech company or whatever, or run your own business. And then the other half of the time you teach or, do research at a university. That's already incredibly helpful and it doesn't cost the university anything. So
I was going to say that model, is it by chance or is it something? So if you look at an engineering company, look at Boeing, look at Airbus, look at Rolls-Royce, look at Shell, look at almost any. I don't think there are very many people there, unless I'm wrong, who are, let's say, they're head of their science, but also a professor somewhere else. They seem to be purely at that company. Whereas I've noticed in tech companies, and I guess your previous role at Microsoft was an example of that, there almost always is a, extremely distinguished scientist like yourself who also has a link to university because it enables them, by definition, that's how they still become distinguished because, they're doing their own research. Do you think this is a model that should be taken more broadly, or is it just something unique to the tech world or with AI? That's the case. I've just noticed this as a trend.
Yeah, we do have some professorships in the Netherlands that are 1 day a week at the university, that are subsidized by a company. So I think it does exist a little bit more broadly. Of course, in the tech world, it gives you also access to the talent pool, which just is a very scarce resource in AI, which may not be the same thing in other companies. So that's one way in which it's already helpful to have some leg in the university. Yeah, and the other thing is that this field is developing so fast. You just need to be at the front, frontier of all of that to know what's going on. And the best way to do that is to have, to have students and, let them explain to you what the new trend is, right? So it's really important that you don't get, sort of how do I say, fixated into your own sort of ideology, but you keep listening to young researchers which pick up the new trends and want to work on new things, and you go with that flow in some sense. So I think there's many advantages of having a foot in academia, also for the company where you work for, in fact.
Yeah. Well, maybe coming to a final question. I think I heard you say in one of the recent talks that you gave that you had underestimated where machine learning could get to. So with that in mind, if we were to fast forward 5 years, where do you think we will be at? And particularly from the AI for science side, do you think there will be a breakthrough, huge change, almost like OpenAI did with ChatGPT, which sort of sent this inflection point? Where do you see us being in the next few years?
That's a tough one. Predicting the future is always extremely tough. I do see a very steady improvement, and this field will grow definitely a lot over the next 5 years. So I see, but that's also because students need to get interested in it. People, new startups need to start. Big tech companies need to get interested in this, which is what's happening now. And so that field will steadily grow. Whether there will be sort of a watershed moment. Now, the reason that happened in the other field is because there's a lot of data available there. So I think in some sense, the weather forecasting is a good example of somewhat of a watershed moment where, these models are much better than people would have predicted. Now, I'm betting myself on materials, clearly. And I think my prediction would be that there's going to be enormous pull or pressure, if you wish, from society to work on, problems in sustainability, because we are running into a wall in this whole climate change problem. We are still increasing our carbon output, since over the last 12% more over the last 5 years, something like this. And there's a lot of countries which still have to go through sort of industrial revolution almost. So I'm not seeing that politics will solve this. And the problem with this is that it's a shared resource, and there might be a dynamics where by the time it's in your face, it's too late because you're past tipping points and all these kinds of things. And humans have the annoying property of only responding to things when it's right in their face, right? When the danger is right there in front of you, when the lion is there to eat you, that's when you run away. And so it's very hard to predict and say, oh, this is going to be tricky, right? And so some people do that, and some governments even do that, but do this at a global scale is incredibly hard. Now, what we will see is the impact of climate change increasing and increasing. And that would mean that this awareness also is more in your face. So it becomes, the awareness starts to increase as well. And that means that people are really going to look for solutions in the tech business as well. So, and there will be more and more investments, and more people will go into that to try to do fusion or carbon capture or, clean energy, all these kinds of things, right? And that will accelerate, and that's a good thing. So in that sense, I think we will find amazing new technologies, and where indeed you could actually find completely weird new materials that weren't imaginable some time ago, but now with these new tools we can actually create them. So I think we'll see amazing things. Whether it's going to be an absolutely watershed moment, that's really hard to predict. But I do think that with the new technology that we're building in AI, and maybe quantum computing as well, in 5 to 10 years, this field will accelerate and produce very exciting results. Yeah.
Do you feel almost that one person told me we've globally, tech companies and startups have hired so many people to work on large language models. Do we almost need to wait for that to plateau, for all those staff to then be given another direction to work on, and then they can double down more on the scientific problems, where for now, I guess most companies are trying to chase the current goal, which is, you know, the large language model type thing. Do you feel there's also a little bit of a resourcing and pivotal moment that we need to shift to focus on the science? Or can they be done in parallel, do you think?
I think they have to be done in parallel because I have no illusions that AGI will be pursued hotly by all these big companies because it's just, I don't know, you can make too much money if you find that this is too you can, how do you say, too lucrative to not do it. But I think there is also a lot of talent in the market, and I have found that a lot of young people in particular, they want to do something that is meaningful with their life. And it's that subset of people that can align their goals in life, contributing meaningfully to society with their talent and make a good, salary on the side. And so I think there will be an increasing group of people who want to pursue these kinds of goals rather than work on advertisement placement or something like that.
Well, yeah, I agree. I hope so. I think it's amazing what machine learning has been able to achieve, but I agree that if we could push all that knowledge and that amazing thing to things that will help the world and society and the average individual, then I think that will be seen as a very positive outcome from all this, rather than, as you said, things that are maybe still useful, but maybe less an impact on society and climate change. So thank you so much. I know you're a very busy man, so I appreciate you taking the time to speak. I certainly learned a lot and I found it very interesting. So yeah, thank you so much.
My pleasure, Neil. It was really fun talking to you.